The last video was about inverses in general. This video is about derivatives of the inverse trig functions. I believe these are the last derivatives I'm going to ask you to memorize, so it's a good thing they're the easy ones. That's a joke. All right, I want you to know that sine of x, as you know, is not invertible because it does not pass that horizontal line test that shows you have a function that you can invert. If I draw a horizontal line, it crosses the function more than one time. But if I restrict its domain, which for the sine function we choose to restrict it from negative pi over 2 to positive pi over 2, then I get something that is invertible. So the sine inverse function is defined as only existing on that interval. So the only outputs for the sine inverse function are going to be the values from negative pi over 2 to positive pi over 2, so that you have a function so that the sine inverse function is a function. Oh, look, I had horizontal lines that showed up. These are the restricted domains for the other functions, just so you are aware. Some people remember them as quadrants of the unit circle, and so the sine function is quadrant 4, and quadrant 1, but it's not the values from 0 to pi over 2 and then the values from 3 pi over 2 to 2 pi. It's the values from negative pi over 2 to positive pi over 2, so that there's no gap in our values. And then for cosine, it's the part of the unit circle that just goes from 0 to pi, which is really a lot easier than the sine one. Tangent shares the same restricted domain as sine does. So just so you know, when we output with the inverse functions, we only get outputs in those quadrants. A reminder that for inverse trig, the input is the ratio that you find at that spot on the unit circle, and the output is the angle that you would input to give that ratio. So sine inverse of negative pi over 2 would be the place on the unit circle where the y-coordinate is negative root 2 over 2, but I want to use the value that's between negative pi over 2 and positive pi over 2, so I'm going to use negative pi over 4 as a name for that angle. Cosine of a half is when the x-coordinate is a half, so cosine inverse of a half would be pi over 3, because that's the spot on the unit circle that outputs pi over 3, and that value is on that cosine part of the unit circle. Tangent inverse of negative root 3 would be the place on the unit circle where the sine over cosine ratio gives you a negative root 3, so it's going to be negative pi over 6. I lied. No, pi over 6 would be negative 1/2 over root 3 over 2. So that ratio would be negative 1 over root 3. I actually want this one. I want negative pi over 3. Okay. So that's what the trig inverse functions do for us. They return the ratio. They are not a reciprocal function. They are the function that undoes the trigonometry. So I know at the top of your note sheet you have all of these derivatives. Those are the ones I'm going to ask you to memorize. And the only one I'm going to prove with you is the derivative of sine inverse. So with this proof, I'm going to start by drawing a picture of a right triangle. And in my right triangle, the angle is going to be called y, because remember, sine inverse returns the angle that gives you that ratio. And I know that sine is equal to x, so if I think SOHCAHTOA, I'm going to give the hypotenuse a length of 1, and I'm going to say that this distance is x. this triangle fits this situation. It's maybe a little bit confusing because x is the sine, but that's because of the setup that we used here. This is a right triangle, so I know that x squared plus this distance is equal to 1 squared. So if I want to solve for that, I know that this distance is going to be 1, the square root of 1 minus x squared. That's just Pythagorean theorem, figuring out the missing side length. Okay. Now, I'm looking at this equation. I want to take the derivative of it. I don't know how yet, or I'm pretending I don't know how because I want to prove it. So I'm going to take the sine of both sides of this equation. So sine of y is equal to sine of sine inverse of x. And then because sine and sine inverses are inverses, they undo each other. So I just get sine of y is equal to x. I can also see that from my picture. I drew a picture that made sure that it showed that sine of y is equal to x. Now that I have this rearranged, I'm going to take a derivative of it, but I'm going to use implicit differentiation because I'm going to treat y like it's a function. So the derivative of sine is cosine of y times the derivative of y, because of the chain rule, is equal to 1. And then if I solve for the slope, I get dy dx is equal to 1 over cosine of y. Now, the only thing I don't like about this answer, I now know what the derivative is that this is in terms of y, and I don't want my derivative to be in terms of y. So I'm going to go to, so ka, that part of my definition, I know that cosine is the adjacent side over the hypotenuse. So for this triangle, which is the triangle we built to describe this situation, cosine of y is going to be adjacent over hypotenuse. So I can replace cosine of y with that radical. So that means, that another way of saying this is that y prime is 1 over root 1 minus x squared. And that's what we think of as the derivative for sine inverse. We don't say 1 over cosine y because that's confusing. What we do is we replace it with a right triangle trig, and we get this really nice equation that gives us the derivative of sine inverse. Notice that in order for this to work, x would have to be between -1 and 1. It isn't going to work at the end points when x is 1 or -1, and that is okay because the sine inverse function is only defined on that interval anyway. Okay, so this is our derivative, and it fits with the derivatives that you have for the other ones. I'm going to go through an example of finding the derivative, and you're going to do the other one. I want to emphasize that when we're doing this, we're going to treat this like the baby. And since I know that the derivative of sine inverse is 1 over root 1 minus x squared, this part of that derivative is the part where we leave the baby alone. So if I take this derivative, I get 1 over root 1 minus squared. And what goes in there is going to be the baby left alone. And then I'm going to take the derivative of that baby, so it's going to be -4x as that derivative. There's not really a nicer way to write this. I could just write -4x over the square root of 1 minus 4x to the 4th. And that is a way of finding the slope of this function at any given point. I'll leave the others for you to try on your own, but I want you to just practice using this new derivative that you have. You have all of the other derivatives as well. I'm going to do this tangent line equation because it has some evaluating in it, and so I want to make sure that you're okay. So in order to write a tangent line equation, I need an x-coordinate, 1 over root 2. I need a y-coordinate, and that would be tangent inverse of 2 times 1 over root 2 squared, or tangent inverse of 2 times a half, or tangent inverse of 1, which is pi over 4. And then I need a slope. So to get the slope, the tangent inverse slope, which is on your sheet, is 1 over 1 plus the baby squared. And then I'm going to multiply times the derivative of the baby, so I'm going to multiply by 4x. The baby in this case is 2x squared. And then I'm going to fill in my value. So I have 1 over 1 plus 2 times 1/2, and then that quantity will be squared, times 4 times 1 over root 2. This becomes 1 squared, so I have 1/2 times 4 over root 2, or 2 over root 2. So my equation for my tangent line would be y equals 2 root 2 times x minus 1 over root 2 plus pi over 4. And that is a totally acceptable answer for an equation for a tangent line. All right. Let me know what questions you have. Feel free to use the questions forum, and I'll be back tomorrow.